Our brains rely on multiple sensory information to evaluate given situations and make decisions about how we will respond. You might not realize it, but when you make a pot of coffee, your brain is receiving signals from a multitude of sensory input in order to assess the situation and respond accordingly. The changes in weight as the water pours into the pot, the location of the pot in relation to its surroundings, the amount of pressure needed in your fingers in order to hold the pot upright, and so on. The brain then takes those multiple components and contrasts and compares them with associated knowledge in order to evaluate what is happening and anticipate what will happen. The two areas I would like to focus on are the somatosensory cortex and the motor cortex. In the motor cortex, signals are sent from layers 5 and 6 down through the corticobulbar tract into the medulla. As the signal travels down, it is routed to the appropriate parts of the body. In the head, it is directed to motor nuclei of cranial nerves, and from there to the musculoskeletal junctures of the head and face. For the rest of the body, it travels through the spinal cord to ganglion cells and then to musculoskeletal junctures. When it reaches these junctures, the muscles respond and a signal is returned to the parietal lobe for updating of the body map and to the cerebellum informing it of the body state. In the sensory strip, external stimuli such as touch, pressure, temperature, and pain are received by specialized receptor cells and sent to dorsal root ganglion near the spinal cord. The ganglion cells send the information up through the spinal cord, through the midbrain, and to the thalamus. The thalamus sends the signal to the cortical layer 4 of the sensory strip, telling your brain what is happening. In 1998, Ramachandran's book Phantoms in the Brain hypothesized that phantom limb experience was a result of surrounding cortical regions encroaching upon the area of the missing limb. A study published in 2001, Reorganization of Motor and Somatosensory Cortex in Upper Extremity Amputees with Phantom Limb by Anke Karl and colleagues, seems to verify this hypothesis. However, a more recent study challenges this theory. In 2006, Catherine Mercier and colleagues completed a study titled Mapping Phantom Movement Representations in the Motor Cortex. The study used similar methods to Anke Karl in 2001, although the results suggested that the plasticity of neurons post-amputation may extend further down the network within the spinal column. It also appears that the corresponding cortical regions of the motor strip may remain intact at their original location. Amongst all the conflicting theories, one thing is very clear. We know about as much regarding the brain as we do our universe. But as long as we work as hard as the individuals suffering from phantom limb and phantom pain, we may one day find answers.